we've made it this far. So in this episode, we're going to go ahead and we're going to look at some of the analysis that some other people have done on a malware sample called HD-Root. So I just want to clarify, this is not our own analysis. We're basically just portraying to you what other people have done and showing off some other people's work. So you can find this show in the same place, same time, most Tuesdays. We usually say like every Tuesday, but look, life happens, things come up. So we try to be here when we can on every Tuesday, but if we're not, just look for Twitter. So you can find us on Twitter at Tradecraft2s, and that's where we always announce the new shows, new links, and whether or not the show's happening. So if you have suggestions on things that we should cover, topics you want to see, questions you have, please definitely hit us up on Twitter, and we'll do the best we can to try and answer them. And if it's interesting, make a show. And if you want to be on the show and ask your question live, hit it up there. Or if you want to talk about some research you did, definitely hit us up.
Yeah, absolutely. And what's interesting is Chris mentioned we're now 20 episodes into Tradecraft Tuesday. If there's anything we learned is the audience is almost always right. We've got great suggestions coming from the audience. At the same time, we've been hit up over and over, just how do we do this? How do we solve this? How do we mitigate it? Can you teach me this training? Feel free to hit us up on our Twitter for that information. A great example of this is over the last several episodes, we've had a handful of viewers that actually reached out and said, hey guys, will you offer a Tradecraft Tuesday or some type of offensive tradecraft class? And at this stage, we haven't developed anything, but as Black Hat instructors, Chris and I both know, part-time training is a huge requirement, huge time suck. So if you guys actually want to see stuff like that, please let us know, because without it, it can't happen. If there is sufficient interest, though, we'd be more than happy to put something together if the community as a whole is looking forward to that.
Yeah. All right, let's jump into some news. We only got a couple things this week. Pony Award nominations open this week. So for anybody who's unfamiliar, the Pony Awards are kind of like they're awards for like research and exploits and things like that for the InfoSec community. They're always given out every year at Black Hat. So if you have some favorite research you thought was really cool, or one of my favorites is the vendor fail, the worst vendor fail, go nominate some things. And then, after the nominations close, they'll have time where you can go in and you can vote on things. So definitely take some time to go check that out. It's pretty cool.
Yeah, that Blue Coat CA seems, CA cert seems right for the Pony this year.
Yeah. Okay, so in other news, Angler Exploit Kit. So we've talked about this in previous shows. It's used by a lot of attackers to drop ransomware and stuff. Basically, it's kind of like Metasploit, and it has a bunch of exploits in it. So when you hit the page, you get exploited, and then they drop their ransomware on you, and all your files are encrypted. It's been really popular since the end of 2013. But basically, a number of people who track exploit kits and all this stuff have said basically over the last couple of days, it basically dropped off the internet. So everybody kind of switched over to this new exploit kit called Neutrino.
That'll be exciting to see how the Tradecraft switches up, what new exploits show up. Also super interesting for a exploit kit to just disappear off the internet. Makes you wonder what's actually going on.
Right. Yeah, I don't know. Maybe their license is expired.
That's what it is. Yeah.
They didn't pay the renewal fee. Dang it.
It's a thing to joke about.
Yeah, I don't know much about news though. What were you saying?
I was just saying that wraps up our news though.
Yeah.
And just as a reminder, this week we're talking about the HD-Root bootkit. And one of my favorite things about talking about the word bootkit versus rootkit versus malware virus and the 10,000 other names is a lot of folks just not familiar with what actually distinguishes each genre between the two. What's interesting about a bootkit is typically, I believe the industry accepted standard would be, it's a rootkit which starts very early in the boot process. Rootkit, boot, bootkit is what you get out of it, right? So it hooks the OS, though, before it's even started. It usually modifies the bootloader to gain some initial execution, and then it might set up follow-on parts of the operating system. Because the reality is it's coming in so early into the operating system's boot process that if it mucks anything up or doesn't fix up things just right, the operating system is no longer going to boot at all. And then I guess maybe you call it a fail kit at that at that point. I don't know.
Right.
Common setups when we start talking about boot kits, we hear a lot of stuff that either affects BIOS / master boot record style partitioning or UEFI / global partition tables. So those are the two standards. And in this example here, the HD root bootkit only targets master boot records. So it's pretty interesting that if you have a newer setup, a lot of boxes by default come loaded with GPT and running UEFI nowadays, you would have been safe for this.
Right.
And what's interesting is UEFI flat out, it makes it more difficult for machines to be infected by a bootkit. The bootloader does some signature verification. Chris, you got anything else to add on that? I mean, hopefully that covered a decent introduction of what a bootkit is.
Yeah. So the only thing I would add to that is so for anybody unfamiliar, the master boot record is kind of is like really the beginning of execution of like a system. So the first thing that's going to come up is the BIOS, and that's going to talk to low-level hardware like your hard drives and stuff. And once it can initialize the hard drive, it's going to jump to the master boot record. And the master boot record is just a little bit of code whose sole job is to load the next piece of code, Really, the boot process of a system is just like a bunch of little pieces of code which do very specific things and then transition to another piece. So that similar mentality is used in this bootkit, where they have several different little pieces, and each piece loads or verifies and sets up the next process. So just keep that in mind as we kind of go through the different parts, because there are several different parts. So figuring out kind of how they all work together is a little bit difficult. If you can, you should follow along with the some of the diagrams in William Showalter's blog post. He has some really good diagrams that kind of show all the different steps of loading this thing up.
Yeah, we'll dive into that later as well, showing these images in case you're not familiar with the research that we're talking about. So moving on, right? We talked about a bootkit. Why is it special? The vast majority of the malware we talk about here on Tradecraft Tuesday, or the hacker techniques, focus on user space. They focus on what happens when the operating system is already up and running, and we don't hear too much about traditional stealth techniques like we used to with the rootkit. And part of the reason this became significantly harder was you have to be able to write, for instance, to a master boot record. You can't do that from user space code. So you actually have to gain access somehow to write to the kernel. And so I think it's probably best that we start this episode out of talking a little bit about the bootkit controller, what it does, how it works, and how it actually enables that bootkit to get in place. So Chris, I'm sure you're familiar with net.exe.
Right.
It's a Windows tool that's typically used for, enumerating Windows network shares. I think you can still do some user account type stuff with it.
Yeah, you can like modify accounts. You can do like a bunch of random stuff, like start services, stop services, like you said, mount shares, add and look at different groups. It's kind of like a catch-all utility for stuff that you would do in Windows that you can access through like the command, the control panel, but net.exe gives you like a command line way to do it. So a lot of system administrators are familiar with this because they'll put like scripts in that run when someone logs in to like mount common shares. So like if you work at a place and they always have like the G drive mounted, likely that's mounted from a script using net.exe.
So what's unique about this, though, is the actors behind the HD root bootkit also were familiar with net.exe. And they said, you know what, to be able to drop and install and manage this bootkit, it's going to masquerade as Microsoft's net.exe, which I found is just kind of really exciting anytime that somebody says, you know what, I could probably make it past unsophisticated defenders, or maybe even just folks that aren't aware, by masquerading as a simple application. So, maybe the first screen sharing we do is we jump in to show, a little bit about what net.exe is. But before that, we mentioned that this bootkit is several stages. So the dropper that we're talking about is the code which is, and Chris, correct me if I'm wrong, this is the code that was initially executed to be able to install the HDRoot bootkit.
Yep.
As well as check the status of it. I think you could actually configure the darn thing.
Mm-hmm.
Alrighty.
Yeah. So when you run this bootkit controller, there's 5 commands. One was like check, clean, install, and info, I believe, something like that. Maybe only 4 commands. And the idea behind it was when you'd run the install command, you'd pass it a path to an executable and say, okay, when Windows starts up, run this executable. So this is kind of interesting because for them, for the attackers, this is a generic persistence mechanism, right? The actual binary that gets started once Windows loads is not included in this bootkit. So they could start whatever binary they wanted. Maybe they have, one backdoor implant that they're going to use, but they might also have others. So that just really allows them to kind of start whichever one they want, which is interesting.
So to augment what Chris was saying there, I brought up the commands. We mentioned that net.exe was a legitimate Microsoft executable. So this example that we're showing here, the command prompt, it shows when the malicious net.exe was ran, you would get this lovely, help output.
Yep.
Although elegantly said, the similarities between this net.exe and the legitimate Microsoft net.exe ended essentially there.
Right.
What's unique is this dropper was signed with a stolen digital certificate. We take a look. We actually have a copy of the certificate here showing that it was stolen from this particular company. Furthermore, as Chris illustrated, there was actually several commands to, manage this dropper here: check, clean, install, and info. And this was the actual utility that, if I understand correctly, would allow HDRoot to be configured with, this is the executable you're going to need to launch upon, next boot up. So Chris, I'm going to stop the screen sharing and turn it back over to you. But hopefully that helped provide a visual description of what we were just describing.
Yep. Cool. So it was mentioned in both the original blog post by Kaspersky and the reanalysis done by William Showalter that the sample that they found was packed. It was obfuscated with something called VM Protect. So in both cases, rather than trying to deobfuscate and reverse engineer the binary, which would have been very difficult, they went back and they found an older sample which wasn't packed. So that's a little bit interesting. You can see from the old sample, which was from 2006, to the new sample, which they found. When did they find this? Was it this year or last year?
I think it was last year, 2015 era.
Okay, so we're talking nine years. You can see the tradecraft progressed, right? At some point, they decided, hey, look, we need to, mitigate some signature detection here. We don't want this to be easily reverse engineered. Let's go and pay a lot of money for VM Protect. VM Protect is not cheap.
Or I guess pirate it, right?
Maybe pirated. I don't know. I've never actually used VM Protect myself. I've looked at several binaries that have been protected with VM Protect, and we'll get into that in a minute here. But it really does a number on the actual code, making it very hard to reverse engineer and figure out exactly what the malware does.
Chris, do you want to provide a visual? I have one here if it's useful at all, of kind of the difference between what a function goes from pre-VM Protect and post-VM Protect, if you think that'd be useful.
Yeah, definitely.
Okay, so Chris mentioned, we talked about it before here on Tradecraft Tuesday. Hackers, the idea behind them is to obfuscate what's actually going on. In this code that I'm sharing right now, so on our right is IDA-Pro, but the idea behind it is it gives you an idea what this function and what the call tree looks like. It's very simple. We take a look. There's a couple, looks like some jump, some compares, and then it returns back to the code. On the left here, though, we see a great example of the mangling that Chris mentioned that VM Protect does. This over here on the right is nice and easy to walk through. I could reverse this probably in 2 to 5 minutes to figure out what it's going on. This here on the left is jump tables upon jump tables of nightmarish code. And this is, re-illustrating or, even reiterating to the point, they realized somewhere along the way that their code was too easy to reverse, and they needed to employ this to prevent their code from easily being detected and reverse engineered.
Right. All right, so let me go into, just to try and give you an example of how VM Protect works. I don't want to get too deep here, but I'll just give you a little bit of an example, kind of high-level overview of what VM Protect does and why it makes this actually really difficult for reverse engineer. So if you want to switch over, Kyle.
Okay.
All right, can you see?
Yep, I see your screen.
All right, great. All right, let's see how this works. I usually use this in my Black Hat trainings, so we'll see if it works here in the Google Hangout, if you can see what's going on. So in x86 or x86-64, the original instruction set, you might have an instruction, in this case we'll call it A, and A is actually an instruction which adds 2 registers. So register 0 plus register 1, right? Okay, so VM Protect wants to obfuscate that and make that not easy. They don't want it to make it easy for anybody to reverse engineer it. So they'll change that and they'll say, okay, well now we have instruction Q, but that's going to equal R0 plus R1. And in the binary, they include their emulator, much like the same way Java includes an emulator. So when you write Java code, you compile it. It compiles down to Java bytecode, which is not architecture dependent. It's a generic form, which is the same as what we're getting here. Right? We're getting a generic instruction here. So the emulator would pull this apart and it would say, well, whenever you see instruction Q, we're going to add R0 and R1, and that's the instruction we're going to execute. So that's why when you look at the what Kyle showed before in IDA Pro, why you have all those jumps and stuff, you're actually looking at an emulator which is reading bytes, interpreting those bytes, and executing different commands. So as far as IDA is concerned, it looks at the instructions and it doesn't see that you're adding R0 and R1. It just sees that there's some random bytes here and we don't know what they are.
That's a really good point, Chris. I know a lot of folks gloss over, kind of the importance of when it calls it VM Protect, it means there's a virtual machine that's processing the actual byte code itself. It's not the processor, doing that. So that was great. Moving on, Chris. So, I mean, we talked about VM Protect. It's converting the original binary instructions into these custom instructions. But when it actually goes to doing its nastiness, do you recall what it does? If I remember right, it starts dropping drivers, right?
Yep. So the first thing that's going to happen is when you do an install, like you said previously, user space is not going to be able to write to master boot record. There's some things you can do with like UNC paths to write to different places on the hard drive, but really the master boot record is something left to kernel protected memory. So what they do is they're going to drop a driver. And there's 2 drivers that come packed in the executable. One is a 32-bit driver and one is a 64-bit driver. The 64-bit driver is signed with a digital certificate. Another one that was stolen, and the reason for this is because on 64-bit, Microsoft requires drivers to be signed, and this was kind of another protection that they added because. In the early days of 32-bit, before 64-bit was really popular, when there was just XP, a lot of malware authors were taking advantage of just loading drivers, and then they had complete access to the system. So Microsoft said, okay, you know what? We're not going to break backwards compatibility, but going forward on 64-bit systems, driver signing is going to be required.
And this is another good reason when we talk about why you should move from XP to any operating system. Essentially, Vista and Server 2008 and above, that became a requirement. So, that's one of those minor security protections you don't think about. But if you look at Server 2003 to XP, which really had problems with, code, unsigned code or untrusted code running in the kernel, From Vista forward, it became significantly harder. Don't get me wrong, there's been plenty of malware that's bypassed code signing, or in this case, it didn't bypass code signing at all. It just stole somebody else's legitimate certificates. This is another good reason why you should continue to keep up, with your operating system's new upgrades, because stuff like this does make a difference.
Right. Yep. So once they have that driver in place, then the bootkit controller can write all of the files to disk, and it does a couple of things. The first thing it does is makes a backup copy of the original master boot record. It overwrites the master boot record with its modified version, and then it makes 2 copies of its something that they call the RK image. And we'll get into the RK image in just a minute. And once all of that's done, then the backdoor is essentially installed. It won't run, though, until the next reboot of the machine.
All right, Chris, I'm jumping down in RK image. Is there anything you want to really talk about? There's a verification piece that kind of makes sure that all the pieces of the bootkit are in place, but do you feel that's overly pressing for this conversation?
No, I mean, it's pretty simple. So when the BIOS jumps to the master boot record runs this little bit of code, which is verifier. It verifies some CRC16s to make sure that all the pieces are still there, and that they are, haven't been overwritten or modified. One interesting piece is if you were infected by this, all you have to do is hold down the Alt key while you boot the machine, and the verifier will detect that, and it will skip, and it won't run the bootkit, and it will just run the original master boot record. So if the Alt key's held down, or if any of the pieces don't match up, they run the original master boot record and boot the clean OS.
Nice. That's a great tip. All right. Now getting on to the interesting part of this sucker,
Yep.
right? So RK image really was where the leakness of this particular bootkit happens. I mean, we mentioned that the whole goal of this is to load some malicious code into the Windows operating system covertly. And without this piece here that we're talking about, this RK image piece, essentially it wouldn't happen. This is what gives initial access, and at the same time, this is kind of what adds some of its stealth. Chris, when we were talking about this earlier before the show kicked off, we saw there was 2 DLLs, right? It was a 32-bit and a 64-bit. They were unobfuscated, right?
No, they're obfuscated. They are XOR.
Oh, that's what it was. XOR. They were obfuscated with an XOR.
Right.
And RK image, if I recall, it makes the decision on, hey, depending on the system's architecture, I need to load the appropriate DLL. For instance, there's no reason to load a 32-bit DLL on a 64-bit system, and definitely no reason to load a 64-bit DLL on a 32-bit system, right?
Right.
And if I recall, this is where some of the loading and modifying of the registry actually happens.
Yeah, this was probably, of all the pieces of this is the most interesting piece. This is also the most difficult transition. So they're trying to transition from running the master boot record, which means you're running in like 16-bit mode, x86. You got to transition to 32-bit mode, x86. And then there's this piece in the middle where like Windows actually does its like core loading. So you have to go from one side to the other side. And there's been a bunch of different ways people have tried to do it. But it's really hard to get into Windows without screwing up how Windows is going to load. So this one actually has some really pretty good bit of work that they put into it, where they actually parse the registry hives off disk. So Windows isn't loaded yet, so there's no API. They can't call, what's that, regkey read or regkey write. Like they can't call any of the Windows API.
32 APIs here at all.
There's no Win32 API because Windows is not loaded yet. So they manually parse and write the registry themselves. And what they do is they take an existing service. Like there's a couple of them, I think. Were they mentioned in William Showalter's or the original Kaspersky report? I don't remember which, but there's a couple of different services, and they modify the service to, instead of pointing to the real service DLL, they point it to one of their special DLLs that gets unpacked from the RK image.
All right, Chris, I'm ready to demonstrate that process now.
Cool.
of how it actually loads this up. So earlier, Chris and I talked about it was a very intricate, delicate setup to be able to pass execution from BIOS to MBR through essentially this native 16-bit operating system all the way into the 32 or 64-bit OS. And so this is Williams' great image. I think it perfectly illustrates both size as well as kind of the logical flow here. We see the bootkit master boot record. Earlier we talked about the verifier, which essentially validates like, hey, was everything properly set up? Because if it wasn't set up, this operating system surely wouldn't be booting, and their whole goal of launching a persistent shady executable would never happen. Jumping into the RK image piece where we just discussed, this is where, we mentioned it does parsing, having to use its own, essentially, I won't say hand-rolled, but native APIs to be able to analyze where, which hive do I need to modify, which service do I need to backdoor, and make the decisions that I need to load the appropriate DLL based on this operating system's, architecture. And then we finally see here this backdoor payload, which will get the execution. Chris, is there any piece you want to comment on this image before I switch it back over?
So that backdoor payload part there, I believe it contains two files. I was unclear whether or not both files were in the backdoor payload or if one of the files was in RKimage, but the DLL that gets loaded by the service and the executable that the user requests to run using the install command are here, and RKimage parses both NTFS and FAT32, depending on which system it's on, to actually write those files to disk. And the DLL that it writes to disk is the DLL that's pointed to by the service that they modified in the registry.
No, that's perfect, man. All right, I flipped it back on over. And probably one of my favorite, I've got a thing for malware persistence. I think it's extremely interesting how execution initially gets started in any operating system. And we see here, we've seen actors backdoor services for years. There is nothing sophisticated about backdooring a service. However, when the execution is transitioned, and what I assume in Williams' diagram, which was backdoor / payload, this backdoor piece is the service DLL, I believe. And what that does is this DLL, it had modified the registry. For instance, we had references to both the scheduler service and the landman service between the Kaspersky report and Williams' report. And it said, you know what it's going to do? It's going to modify the service so the DLL that's actually going to do the loading of the malicious payload, the piece that's specified to net.exe, it's going to cause that to get loaded in two different ways. I won't dive too deep because it gets fairly technical, but the idea behind a DLL is DLLs have multiple entry points, kind of like how a library could have multiple function calls. And why this is important, and there's a fantastic diagram that goes with this, is the actors behind this realized what they could do is they could spawn the backdoor DLL a certain way to prevent essentially all of the code being executed. And what that does is it allows the backdoor thread to get spawned. It creates its process that causes the shady payload to get its execution. But at the same time, it's able to call essentially a different entry point. This is the difference between DLL main and service main. And when service main actually gains execution, it reverts the registry key back to the schedule service or the landman service and allows proper execution of those services to be properly executed, so they're not losing execution of whatever critical service that they backdoored. And Chris, I find that extremely elegant. I mean, what are your thoughts on it?
Yeah, I mean, it's pretty good. I mean, a lot of people might have gone the route of like trying to create another service or whatever, because like you said, one of the things you don't want to do is like take over a service, but that service is probably important, so you want it to continue running. So like in this case, they load up as that service, they fix all the registry stuff back, and then when they exit after they've spawned the payload, basically the service manager sees like, oh crap, this service exited, that's not good, I better restart it. And when it goes to restart it, it rereads the registry, loading the original service, so everything runs again as intended.
All right, so I'm bringing it up here real quick, present it to everyone, just because it's always neat to see a diagram rather than have people talk to you about it. So just walking it through here earlier, we mentioned, hey, here's the Windows loader. It passes execution to DLL main. At this point, it spawns off a separate thread. This is what actually runs, that malicious payload. From there, it it suspends itself because there's some synchronization from what I understand going on here. It waits for it puts a flag in place to indicate, hey, I've spawned my shady payload. And at this point, it suspends itself to enable the service main to be called simultaneously, which reverts the registry key, waits for that flag that has now been set globally, and then resumes the thread for execution. Chris, do you have anything else to add before we move on?
No, I mean, I think that's a pretty good, diagram that shows how the two different pieces come together, one waiting on the other.
All right, and really that really encompasses the effort or the investment the actors behind HD Root Bootkit put into this. It was all about making sure a payload gets executed in a covert fashion. I know Chris and I glossed over. It's very hard over a video like this to get in depth and actually articulate just the amount of time that this actor had to put in place to be able to properly parse the registry hives with native APIs. I mean, this is a significant investment. So I know there were some comments back in 2015 that came out that said, oh, this was kind of unsophisticated. My thought is these actors has put significant amount of time into this. And although, it's not super leaked in the sense that it doesn't exploit UEFI to load into GPT, it only supports MBR, I think they clearly put their time into, to deliver an elegant technique that is going to go undetected on most customer or most networks that defenders would have to protect against.
Oh, yeah. I mean, this is not Stuxnet, right? Like, Stuxnet was very, very advanced. But this is easily in the top 5% of malware. I mean, if you look at the majority of malware is really terrible, right? They just create a service or they use a run key or whatever, right? These are not new techniques. These are not advanced techniques. Like you said, these guys had to write code to parse registry hives, parse NTFS.
Support for FAT.
FAT32 because it's it works on Windows XP. So this is not something that somebody just threw together in a couple hours and we're like, call it good. There was a decent amount of effort here, and like I said, I would put this in the top 5% of malware for how advanced it is, I guess.
And not to mention, to even load this malware, they had to steal certificates from 2 other companies to ensure that they could load code into the kernel to even begin this technique.
Right.
So, I mean, I find this, very exciting when it comes down to it. How about for defenders? What can defenders do on this, Chris? I mean, this is a good example, I would say, of like a nation-state level capability. Whether it's actually a nation-state actor, it's definitely a sophisticated actor. There's no arguing about that.
Right. Yeah, I mean, what can you do? Well, at some point, whenever you're ready, refresh your hardware and try to buy hardware that supports UEFI. But the second thing that you have to do, even if you have hardware that supports UEFI, you're likely going to have to do a reinstall of Windows to enable UEFI, and you're going to have to go into the BIOS and add the certificates to say, like, these are essentially approved pieces. So for anybody who's not familiar, UEFI basically creates a chain of trust from the BIOS to the master boot record to the Windows loader to the drivers to everything. Each piece verifies the next piece before it will run it. So as a defender, if you can enable UEFI, that will basically stop this technique in its tracks.
Well, Chris, you kind of stole my thunder because I was going to kind of go through there. Like, we sometimes on the show talk about the super elite. You must have this sensor across all endpoints to be able to identify these anomalies. But I think this is one of those examples that a good old-fashioned system administrator that just cares to know enough about his hardware. What are the capabilities? What is the difference between BIOS and UEFI? What does my processors now have? In forms of mitigation. And yeah, there's exploits for UEFI, but you've just raised the bar that much higher for your actor to be able to get on your system and accomplish their goal. So I think this is a great win for, whether you're a system administrator, aspiring cybersecurity, whether you're a student or actually a practitioner at that point. I think this one boils down to, as long as you're doing tech refreshes every 3 years, like a lot of companies tend to do, bringing in new hardware, I think as long as your hardware is configured right, sadly, I think this super sophisticated technique stops dead in its tracks if you're running UEFI.
Yeah. I mean, things like this were pretty common back in early days of Windows XP and stuff. But this is exactly what UEFI was created to stop. So,
yeah, we missed it in our news today, but Intel provided that tech preview of their control execution prevention that is looking to stop rot. That's another example of understanding what your hardware, your processor, your motherboard, the BIOS, or a UEFI setup. You know what they are. You can mitigate some of these effects extremely well.
Yep.
All right, man. I don't have any more ranting other than I think this is very exciting. I do want to thank both Kaspersky and William for being able to provide this absolutely fantastic analysis. It would have taken way more time to be able to actually do this deep dive and reverse this ourselves. So
Right.
Without their blogs, we wouldn't have been able to do this. Also, like to thank those that actually put us on to the new blogs that came out. This was a good example of somebody saying, hey, I'd like to learn more about HD Root Bootkit. Voila, here you go.
Right. Yeah, so we'll make sure in the show notes we link to both the original blog post by Kaspersky and the new blog post by William, as well as William's GitHub, which contains a ton of information, like all the files he analyzed. There's IDA Pro databases up there, so if you have a copy of IDA Pro, or even if you just go and download the trial, you can open them up and you can take a look and see what VM Protect looks like, and just try and get an idea for yourself of if you're aspiring, what kind of stuff would you be looking at?
Cool. With that said, this wraps up our 20th episode of Tradecraft Tuesday. Thanks again, guys, for hanging out with us. Once again, I'm Kyle Hansloven. This crazy guy here is Chris Bisnet, and thanks for joining us this Tuesday.
Yeah, hope to see you for another 20 more.